All right, so starting chapter 8 with covalent bonds. Here again, stability. Everything wants to be stable. Just kind of like we said, electrons are lazy, atoms are lazy. They don't want to work much, they want to stay stable. And that is related to its energy. The lower the energy, the more stable the atoms are. Metals and nonmetals, so there's ionic from last chapter. Metals and nonmetals are going to transfer electrons. They're going to gain electrons if they're a nonmetal. They're going to donate electrons if they're a metal. And that's ionic bonding. Another way that they can be stable is by sharing electrons. So there's no actual donation. It's still going to result in noble gas configurations, and that's going to be a covalent bond. So a covalent bond is not ionic. So we're looking at something totally different this chapter. The compounds will be different. The properties will be different. The chemical bond that results from sharing, so that's a huge word this chapter is sharing. They're going to share electrons, is a covalent bond. Ionic is formed by transferring and opposite charges. Covalent is formed by sharing. And when they share, you form a molecule. So if you've heard that, and we talk a lot about that probably in biology. If you've talked about sugar molecule, fat molecules, protein molecules, these are all covalent bonds. So sodium chloride, the salt that you put on your French fries, is a compound. It is not a molecule. Only covalent things are a molecule. And the majority of covalent bonds are between a nonmetal and another nonmetal. So not very many metals are involved in covalent bonds. Di means two, so diatomic molecules, which I want you to start memorizing these. So if you look at group 7, iodine, chlorine, bromine, everything pretty much in group 7 is diatomic, I2. So if I tell you that I have iodine in my closet, its formula is I2. The oxygen that you breathe is O2. Nitrogen gas is N2. Fluorine is also in group 7. So everything in group 7, hydrogen, nitrogen, and oxygen are the main diatomic molecules that we'll look at. And they exist in nature like this because they are more stable. And what happens is you'll have two atoms that come together, and you can kind of see what happens is the repulsive force and the attractive force balance out, and we'll talk about how that happens. So, in a covalent bond, here again, the most stable arrangement exists at a point of maximum attraction where things are held closest together. And what happens is they're going to share an electron. And when we talk about the electrons, they're going to have names. So they're looking at fluorine. So if I have this fluorine, fluorine has how many valence electrons? 7. 1, 2, 3, 4, 5, 6, 7. And this fluorine has 7. And what happens then is they share those two electrons. So these electrons that are in the middle are called shared electrons. And all of these on the outside then are called lone pairs. So this is a lone pair. This is a lone pair. This is a lone pair. These are called shared electrons and also bonding electrons. So what happens is the bond occurs where those two electrons are shared. And another thing that I want to point out now, which we'll talk about later, is when you make a bond, eventually we're going to show the bond as a line. So wherever you see a line, what's actually there? How many? Two. Every time you see a bond, there are 2 electrons that are shared in that spot. So, for example, if I have carbon, carbon can have a triple bond. That would be called a triple bond. How many electrons do those 2 carbons share? 6. 2, 4. Everywhere there's a line, there are 2 shared electrons. So in that case, there would be 6 electrons that are shared. So when only one pair is shared, which is probably the most common, it's called a single covalent bond. And all of your diatomic molecules have a single covalent bond. F2, N2, O2, H2. They share the 2 electrons that are in the middle. So here's the bonding pair of electrons, or the shared pair of electrons. That's where that bond takes place. So when we draw these, I'll either have you put dots, or I'll have you put a dash. Computer models that draw electrons, you can see something like this. But I won't have you draw the spheres. I will either have you put dots, or I'll actually have you put the bond in between. Lewis structure is the structure then that we'll use. Down here at the bottom it talks about that. Lewis structure, use dots or a line to show where that bond is at. And real short one here. Lewis structure, dots or line are used. Halogen group 17 elements have 7 valence electrons, and they can form single covalent bonds with atoms of other nonmetals. Because, we'll go back to fluorine, 1, 2, 3, 4, 5, 6, 7. It has that one empty spot, so therefore it can bond with one thing. If I have carbon, carbon has how many valence electrons? 4. So how many other atoms do you think carbon can bond with? How many? 4. So it has an empty spot here, empty spot here, empty spot there, empty spot there. Carbon can bond with 4 other atoms. So group 17 can share with 1 other element for the most part. Atoms in 16 can share with 2. Very important for water. So water has an oxygen atom in it, which is in group 16. 2, 4, 6 valence electrons. 2 of them are not paired up already. So there's a spot here and a spot here. So a hydrogen can bond here and a hydrogen can bond there. And that's how water is formed. Water is covalent. Water is a molecule. If we look at group 15, nitrogen is at the top of 15. So nitrogen has 5 valence electrons. The one side is paired already, so they're not going to share. So it has 3 bonding sites, so it can bond with 3 things. And then here's the carbon that I already talked about. 4 spots, so it can bond with 4 different things. So depending on what group the element is in will depend on how many places that it bonds. Then when it bonds, there's going to be different types of bonds. There's sigma bonds, which are the most common, and then there's pi bonds. Sigma bonds, sigma, single. That's the easiest way to remember it. So there would be, if I have hydrogen, there's going to be a single bond, a single bond. Anywhere where they're sharing, there's going to be a single sigma bond between each pair of electrons. So sigma single. That's the easiest way to remember it. So here, patterns on glass, and I do like this because it uses real information, can be etched using hydrogen fluoride. So draw the Lewis structure for hydrogen fluoride. I like using my markers because then I can use more than one color. So hydrogen, how many dots? 1. And this is an easy one. Fluorine, how many dots?
7.
So, what happens? They share here. So, really, this hydrogen has its own, and this one, which gives it 2, which makes hydrogen full, because hydrogen only has the first s orbital. Fluorine, wrong color, 1, 2, 3, 4, 5, 6, 7, will have one of its own, and then the hydrogen here again. So they're sharing each, but it makes them full because these 2 electrons move back and forth. So to actually draw that, I would put H dot dot F, 1, 2, 3, 4, 5, 6. So now my hydrogen is full, it has 2, and my fluorine is full, it has 8 electrons, and that's that octet rule that we try to get to. And I'll stop there for now.